So, this is about the time dilation, and basically it's about these two graphs. But this Pythagorean theorem is a bit tricky because it makes two inertial reference frames together. So it will feel difficult to understand. But let me explain it again. So for this line L and also this line, the time need to measure using two synchronized clock, C1 and C2. So the time for these two segments should be the same and note as delta t, which means that at the very beginning, these two clock is at the 0, and black try to move from here to there, and of course you need two clock to read the starting time and the stop time, because this is far away, because v is sufficiently large compared to the comparable to the speed of light. So this distance should be very large, and as you know, the information cannot be transmitted faster than the speed of light. So you cannot at this point and read the clock here. So you need the clock to read the start time. You need C1 to read the start time here, and you need another clock C2 to read the stop time there. So this is delta t. You will use delta t for this one and also for counting this one. So it is delta t equals 2L over C, 2L over C. And this is this segment should be V times delta t. However, this line is a bit different. This line is actually seen by the reference frame at this object. So you can consider there is original one is the so-called stationary reference frame, which we used to. So you can easily to imagine, oh, this one is L over delta t, this one is L over delta t, this one is V times delta t. However, for this one, the d is actually seen by this one. The point here is that for example, at t equals 0, b is here, and it also try to emit a light to the mirror, and it start to move. So, for example, at this point, when b moves to this point, the light goes to here, and when he moves to this point, the light touch the mirror, and so on until black move to here, the light reflected back. So suppose this one is x-axis. So the displacement at x-axis for the light and for the light and B should be the same at any time. Otherwise, B cannot receive the light when the light comes back. Okay, up to now. Okay, so imagine there is another reference frame moving together with the object B. So at time equals to 0, there is an inertial reference frame at here, and at this time there is another reference frame moving with the speed v, because black is moving with the speed v, right? So at t equals to 0, the light is also at 0, right? And at this point, he will feel that the light is here. And when he moves to, for example, when he moves to here, he will feel that the light moves to here. So that for B, he will feel that the light only goes up and goes down at the moving inertial reference frame with the speed v until he goes to the final point. He moves back. Okay, up till now, okay. So for the object or for the moving reference, inertial reference frame, the distance for the light it move is 2D. So we have 2D here, and because this object and the reference frame don't have any relative motion, so that they share the proper time, which means that this clock C also plays at B, so that it moves with this stuff. So for the start time for B and the stop time for B, it uses the same clock. So it should be the delta T0. Up till now, is there any question? So the postulate of the relativity comes because for the stationary reference frame, the light moves for 2L. However, for this moving reference frame, the light moves for D, so that the time should be different for them. So this time should be shorter. This time should be larger. This time should be larger. This time should be smaller, so that the speed of light should remains the same. And after we write the Pythagorean theorem, we'll have this one is 1/2 Vt or in the parenthesis and square, and this one is d squared L squared. So we substitute L into here and d into there, so that we will get delta t equals delta t0 over square root of 1 minus v over c squared. So that how does it come from? So a simple rule is that if you need two clock to really measure the time, it would be the delta t. For this one, they don't have relative motion, so that you can use only one synchronized clock to measure the start time and stop time. So this one use the proper time, delta t0. And for this one, you use delta t. So in one sentence, it will be like this. You use one clock, then it is the proper time. You use if you use two clocks, that is delta t, and it will have a time dilation. So it means that for the object B, it passes through a shorter time. But when you are stationary, you look at the black, you will feel that it moves for a longer time. This is what is implied in the time dilation. And actually, we can see something like here. Actually, we have so-called four-dimensional Euclidean space. So in 1905 to 1906, Poincare. So some of you are mathematics students, so you should know about him. He proposed the famous conjecture of Poincare, and the mathematician spent 100 years to really solve it. So he proposed, and as you remember, Einstein also proposed the special relativity in 1905. So roughly at the same year or 1 year later. So he mentioned that the time would be the imaginary fourth space-time coordinate, IC omega t, IC omega t. So c is the speed of light, I is square root of 1. So you have XYZ and also ICT as the fourth space dimension. And when you consider the Maxwell equation and the wave equation, you should see the Maxwell equation in the last lecture. Also, I just derived the wave equation from Maxwell equation like this, and you will see actually yeah, here. So the equations are named after the physician and mathematician Maxwell, who published an early form of the equation that include Lorentz force law between 1861 and 1862. Maxwell first used the equation to propose that light is an electromagnetic phenomenon. So at that time, roughly 50 years before that, he proposed that the light is an EM wave. And one interesting stuff, you can feel that. So we have the wave equation like this. Wave equation for the E view or B view, they look like this. Okay. So if we write the Laplacian in the XYZ domain, it will be look like this. Partial XE, of course, is a vector, but I just don't write more about it. So Laplacian of E should look like this. Second derivative of E with respect to XYZ and sum them together. And we move this term to the left. It will be something like this. If we just set U equals to ICT, then it will look like X, Y, Z plus U. So you feel that mathematically X, Y, Z, and U are symmetric, which means that ICT should be a space dimension. However, the time is in the imaginary domain of the space. Imaginary domain. So these are real dimension. This one is imaginary dimension with a scaling factor C between them. Okay. So we have another sample problem about this property. So this is called the twin paradox. The tricky part is that it is a little bit different from this case. Because for this case, the starship actually go back to the original point. But for this one, black goes straightly, so that it needs two synchronous clock to measure the total time. So this is the tricky part of the twin paradox. And as you see here, the problem tells you to neglect the effect due to the acceleration involved in stopping, turning, and getting back to the speed. And here, it uses a trick that here's a mirror here, so that you can emit a light and it can reflect back. However, if it is a starship, it is not really the same. It really needs some acceleration going from here to there and going back from there to here. So there's a bit tricky, I think. But if you can exchange the real space domain to the imaginary space domain, maybe it is still okay. I'm not really sure. I'm not really an expert of the relativity, so just ignore this effect and we accept the answer look like this. So the time for the guy on the Earth is longer than the one on the starship. So one point to emphasize is that this 10 year is something like so it has a starship and this is the Earth. Oh, the starship is too large. So it goes for 10 years. But this 10 years is measured by a clock putting on the starship. Something like this. So the clock put on the starship doesn't really have a relative motion with the starship itself. They move together so that they share the proper time, 10 years. However, the guy on the Earth here have a relative motion with the starship, so that the time it feels to this stuff is delayed. So that's what it means. 447 years is for this poor guy. And 10 years is for the one on the starship. Okay, until now, any questions? So we have another sample problem. Okay, the elementary particle known as the positive Kn is unstable in that it can decay into other particle. Although the decay occurs randomly, we find that on average the lifetime is 0.12 microsecond when stationary. That is when the lifetime is measured at the reference frame of the Kn. If it moves with a speed 0.99z relative to the lab reference frame when Kn is produced, how far it can travel in the frame during the space-time according to the classical physics. What is the reasonable approximate for the speech much less than c, and according to the special relativity. So we need to calculate for two cases. The first case is using the classical physics. We assume the time is absolute, and then we calculate how long it can move. And the second case is according to the special relativity, so that the speed of light is constant, so that time would be delayed when it moves very fast. Okay. So for the first case, it would be very simple. DCP, classical physics, is nothing but V times delta T. And it moves with 0.990, 0.990 times 2.998 times 10 to 8. So in relativity, so we will usually use 2.998 times 10 to 8 rather than 3 times 10 to 8 because the speed is quite close to, usually we will discuss something close to the speed of light. So this tiny error could make sufficient error to the calculation, so we'll care about it. But for optics, for other stuff, well, less than 0.2% error or less than 0.1% error is not really great stuff. So sometimes we only use 3 times 10 to 8 meter per second for the speed of light. And the lifetime is 0.1237 microsecond, 0.1237 times 10 to minus 6. So we can move for 36.7 meter. So that is the answer for the first case. So for the second case, we consider the special relativity. So this is also V delta T. However, this T is a little bit different, which is V delta T0 over square root of 1 minus V over C all square. Something like this. So it would be something like also 0.990 times 2.998 times 10 to 8 times 0.1237 micro over 1 minus 0.990 square, something like this. So it actually can move 258.7 meter. So which is roughly 6 to 7 times longer. Because this one is really close to the speed of light. So the relativity effect is very sufficient to consider. Relativity will use this number rather than 3 times 10 to 8. But actually, in the quiz and exam for this course, I will just give you the number, and actually you just press the calculator. So I think you, for all the case, you can use this number. So up till now, any problem? Any questions? Any questions? Okay, so the next effect is the length contraction. So it is a pair phenomenon with the time dilation. So with the time dilation, you can expect the length is contract as well because c is constant, and it should be L over delta t. So if the time is delayed, the length should also be contract so that they can match that we have a constant speed of light. So for this case, as the time is delayed, so we have a delta t equals delta t0 over square root of 1 minus beta square. So we can expect that the length should be contract. So it would be equals to L0 multiply square root of 1 minus beta square, or L0 over gamma. So it says that does a moving object really shrink? Really is based on the observation and measurement. If the results are always consistent, if no error can be determined, then what is observed and measured is real. In that sense, the object really does shrink. However, a more precise statement is that the object is really measured to shrink. Motion effect by this measurement thus reality. Which means that, for example, with this length from XA to XB, which is L0, if we measure it when we are stationary, which means that we have a how to say. So if you want to measure the front to the back length for a penguin while it is moving, oh, it should be this one. Oh, I see. So if it is not really moving, or this ruler is moving with the penguin, so actually we measure it at the same time. We measure it at the same time for XA and XB T0, so that we know the length of the penguin. And this is actually the proper length, because the ruler and the penguin does not have relative motion, so that this is the proper length. However, if the ruler is put stationary, then we'll find that at T0, we measure the back of the penguin, and at T1, we measure the front of the penguin. So as this time should have a time dilation, then when we consider, this one is not L0, this one should be L, should be relative to the gamma factor or the Lorentz factor. It mentioned that if you want to measure the front to back length of a penguin while it is moving, you must mark the position of its front and back simultaneously in your reference frame. So in A rather than at different time as in B, how to do that is not trivial because it is actually moving. So it is moving in a speed v. So when you look at this and you try to move and you look at this, you don't actually know how long does it moving, or you need to know the time, but you also know the speed here. In the textbook, there is another example which is easier to understand. It mentioned that there is a train. There's a train moving across the station. If you measure it on the train, so the ruler is moving together with the train. So this ruler will not have a relativity effect. However, if you really need to measure it on the station, which means that when the train arrives, so you stand here to read. This is T0. So when you see the front of the train, and as it leaves, you mark another time. You mark another time. This is say T1. So that when you observe this train moving at speed v, this time should have time dilation. This one should have time dilation. And does it have time dilation so that when you try to calculate back its original length, you need to multiply the same factor gamma, or you should divide the same factor gamma, rather than so for this case you multiply here, but for here you need to divide the same factor here so that everything should match. Here we can also use the same rule if the ruler is at the same if the ruler is moving with the object you want to measure, then that is the proper length if the ruler is, for example, stationary and the object is moved at speed v, then you measure this, the length should be L rather than the proper length. So here is another example. So steady at point A, steady at point A here. And Sam, spaceship, Sam is on the spaceship of proper length L0, proper length L0, which means if it does not move, the length is 230 meters. Pass each other with constant relative speed v. Steady measure time interval of 3.57 microsecond. 3.57 microsecond for the ship to pass her. From the passage of the point B in figure A to the passage for the point of point C, point B, point C, because steady at this point. So in terms of C, what is the relative speed v between steady and the ship? Well, so which means that steady measure time interval of 3.7 microsecond, which is the delayed time. So actually here we can write v equals L over delta t, and so this is the delayed time, and this is the proper length. So that we must either make it to the, we can either make this one to the normal length at set its reference frame, or turn it into the proper time. So we can do it like this: L0 over gamma over delta t. Because we have L0, so we have L0 over 1 minus V over C squared delta t. So we multiply delta t on both sides. We have V delta t squared equals, and take the square on both sides. So we have and also we divide it by L0, so that we have something like this, Then we can move this term to the left side and factor v square out, so that we have a delta t over L0 square plus 1 over c square multiplied by v square equals 1. So finally we have v equals to delta t over L0 square plus 1 over c square, and this is to the minus 1 over 2 power. And finally, we can write it as L0C over square root of C delta T square plus L0 square. So it's just some algebraic calculation. And we substitute all of them inside 230C square root of 2.998 times 10 to 8 times delta T is 3.7 times 10 to minus 6 square plus 230 square. So all in the square root. And the final answer will be 0.210C. And actually, this speed is not really fast. It's not really fast. If you just calculate it by or if you just calculate gamma when V over C equals to 0.21, it is something like 0.978. If you don't really need a very high accuracy, so this is just 2% different. 2% different if you don't consider the special relativity effect. Which means if you just calculate L0 over delta T, you will have the speed is, if you're just using L0 over delta T, then you will calculate the speed to be 0.215C. So the error is not really large. That's why we need to consider the C to be 2.998 times 10 to 8, because when the V is so large like this, the error is not really large. But if you just let C equals to 3.10 to 8, then you already have some error. Okay, next one, caught by surprise, a near supernova. 超新星 supernova. You raise away from an explosion in a spaceship, hoping to outrun the high speed material ejected toward you, your Lorentz vector relative to the inertial reference frame of the local star is 22.4. So speed would be really fast. To reach a safe distance, you figure out you need to cover 9 times 10 to 16 meter. Ooh, very long distance. As measured in the reference frame of the local star, how long will flight take as measured in this reference frame? So it already tells you that the Lorentz vector is 22.4 if you don't consider relativity effect. So the answer will be 22.4 times larger, or 1 over 22.4, something like that. Okay, so first of all, we calculate what is the speed. So we have 22.4 equals 1 over 1 minus c over v squared, so that we can have v equals to 0.999 c. 0.999 c. Then we calculate the time. As you know, you figure you need to cover 9 points as a measure reference frame from the local star, which means that this is the proper length. This is the proper length. We just say as a measure in the reference frame of local star. No, yeah. To reach the stage is significant, you need to cover mention this frame of the local star. Oh no, this is not the proper length. 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 Because actually you are moving at a very high speed v. So comparing to the reference frame of the star, you have a relative motion, so that this should be L rather than L0. This will be L. This will be L. So here we have L over V, which means 9.00 times 10 to 16 over 0.999 times 2.998 times 10 to 8, and this would be this would be 3 times 10 to 8 second, and is 9.52 year. So on the planet, you feel that you 9.52 year, then the starship go to a safe space. And question B, how long does the trip take according to you? And actually you are on the starship moving at V. So that this is the proper time, because that clock is put on the starship, and the starship and the clock doesn't have a relative motion, and it should be the proper time. So we can just simply divide the delta t. We just calculate by gamma, then it will be the proper time. So it will be 9.52 over 22.4, which is 0.425 year. So which means that from the panel, you feel that it takes 9.52 years to really really go to the safe space. And actually, when you are on the Starship, you feel like you only use less than half a year. Okay. Any questions?